All right, welcome to the Explainer. Today we're diving into a really wild idea. What if the code that keeps us safe online and the code that literally builds life itself are actually the same thing? We are going to connect the invisible world of cryptography to the very building blocks of biology.
So let's just jump right in with this question. What if that algorithm protecting your bank transfers and the protein that helps you digest your food are secretly running the exact same program? I know, it sounds nuts, right? These two fields couldn't seem further apart.
Okay, first things first, let's talk about something we all use every single day, even if we don't realize it. You see that little padlock icon in your web browser? Well, behind the scenes, an algorithm called SHA-256 is doing some heavy lifting. The best way to think about it is like a superpowered blender for data. It takes anything, a password, picture, you name it, and churns it into a unique, one-of-a-kind code, a digital fingerprint. If you change even one single letter of the input, the fingerprint becomes totally different. That's how we know our data is secure.
Now, we've always just thought of SHA-256 as that, a data scrambler, a security tool. But what if that's not the whole story? A theory, coming from what's called the Nexus Framework, paints a totally different picture. It says SHA-256 isn't just a mathematical recipe. Get this, it claims SHA-256 is actually a tiny, hidden computer. And the data we put in, that's not just data. It's the program this little machine executes.
Okay, so if it's a machine, what's actually going on under the hood? How could something like that work? Let's take a quick peek at the architecture this framework lays out. So according to this framework, this little machine has all the parts you'd expect. It's got some little memory slots called registers. It has a tiny built-in instruction manual. It's firmware. It even has a clock that ticks 64 times to run whatever program you give it. So when you feed it your password, it's not just mixing it up. It's treating that password as a set of commands and running them. And that final string of code, the hash, that's not a random jumble. It's the final snapshot of the machine's memory, a perfect record of the program it just executed.
And here is where things get, well, really weird. The machine's most basic commands, its opcodes, aren't described with computer terms. One of them is called majority, but the framework describes what it does as an inward fold. It's like it's literally taking information, increasing it, compacting it in on itself.
And then you've got its partner, the choice command, which is described as an outward branch. This doesn't sound like math. It sounds like choosing a direction, like a fork in a road. So you've got these two fundamental actions, folding in and branching out. Remember those two. They are absolutely key. And look at this, the theory even provides these simple little diagrams for these actions, the inward fold and the outward branch. Just tuck those shapes away in your brain for a minute because we're about to see them pop up somewhere you would never, ever expect. All right, so let's hit pause on computers for a second. We're going to do a hard pivot now, from the world of silicon to the world of carbon. We're jumping into molecular biology to look at one of the biggest, oldest questions out there. You know, for literally decades, scientists have been banging their heads against the wall over the protein folding problem. And this isn't just some niche puzzle, it is one of the most important unresolved challenges in all of biochemistry. So here's the mystery, right? A protein begins its life as just a long, floppy chain of amino acids, like a piece of string. But to do anything useful, it has to fold itself into an unbelievably complex and specific 3D shape. Now, the number of ways it could possibly fold is just astronomical. We're talking more than the number of atoms in the known universe. And yet, it finds the one single correct shape in a blink of an eye, every single time. How on earth does it do that? So the standard explanation is all about physics and chemistry, right? The idea is that this little ribbon just kind of wiggles around randomly until it settles into its most stable, lowest energy shape. But this Nexus framework, it says, nope, not even close. It claims protein folding isn't random at all. It's a rigid computational problem, meaning it's a predictable step-by-step process. The protein isn't searching, it's executing a program. And this is where it all comes together. This is the bridge where the digital world smacks right into the biological one. Okay, look at this. This table lays out the core claim, plain and simple. It proposes a direct one-to-one relationship. That 1D string of amino acids, that's the input data for the program. Those physical mechanics of how the protein folds and branches, those are the inward fold and outward branch opcodes we just saw. The final 3D shape of the protein is just the output. The theory is saying that biology is literally running a crypto algorithm. It's wild. And right at the core of this whole thing is a single, kind of strange number. The framework says this number, about 0.35, which it calls a harmonic constant, is basically the universal trigger for a fold. The idea here is pretty cool, actually. Think of that protein chain like a stretched out rubber band. As it forms, there's tension all along it. And when the tension in one little spot builds up to be about 35% of the total tension in the whole chain, it hits a critical tipping point. And when it hits that magic number, snap, a fold happens. It's a purely mathematical switch for a real-world physical event.
But hold on, because this doesn't just stop with proteins or computer code. This is where the theory goes from biology to, well, the entire universe. It expands into a whole cosmology.
Now, this next part is a real mind-bender, so stick with me. The theory's ultimate claim is that the universe isn't actually computing things on the fly. Instead, reality is a static, pre-existing library of every possible state of everything. A better way to think about it might be a video game. The entire map, every character, every outcome is already on the disk. You're not creating the world as you play, you're just exploring a pre-existing file. The theory says reality is like that.
So in this model, a protein doesn't figure out how to fold any more than your computer figures out what's in a file. That sequence of amino acids, it isn't a list of instructions. It's an address. It's basically just a zip code in this huge cosmic database. The universe just looks up that coordinate and pulls out the final, pre-made, folded shape. Folding isn't an act of creation, it's an act of retrieval.
And this, of course, leads us to a really profound and honestly kind of startling philosophical question. It really forces us to rethink what it even means to invent something. I mean, just let that sink in for a second. If this is true, it means we didn't invent SHA-256. We didn't create it. We just stumbled on it. Like finding a strange alien artifact. It suggests we accidentally uncovered a fundamental piece of the universe's operating system, a geometric language that biology has been using since the dawn of time.
So, why does any of this matter? What's the big takeaway here? Well, if any of this is right, it totally changes our understanding of everything. It means computation and biology are just two dialects of the same universal language. It suggests that life might not be some happy chemical accident, but a computational certainty baked into the laws of physics. And it means that our best technology might just be us, clumsily rediscovering a logic that's been running the show all along.
So we'll leave you with this question to chew on. If a simple security algorithm could hold a key to understanding life itself, what else is out there, hiding in plain sight, embedded in the technology we build and use every single day that we think we understand, but don't understand at all?